Which type of forces are stronger? Intermolecular or intramolecular? Intramolecular are stronger because they are bonding forces. Okay? Intramolecular and intermolecular forces. Which ones are stronger? Intramolecular. Because intramolecular are bonding forces, while these are forces in between different molecules which are weaker. More or less you can have an intramolecular force or a bonding force of maybe around, let's say, 250 kilojoules per mole to break one of these forces. That's a number, okay? And you can have around this one like 25 kilojoules per mole. So which one is stronger? Bonding force. By a little bit or by a lot? By a lot, okay? A lot. Okay, like there's not even a comparison. These are the forces that hold molecules together. Okay? So if I have HCl, is there an intramolecular force in HCl? Is there an intramolecular force in HCl? Yes. It is a bonding force that is holding this hydrogen to that chlorine. It is a bond here. Okay. Is there any intermolecular force right now in that HCl molecule that you on the board? No, because we need another HCl molecule on the board in order for that to take place. So one side of the HCl is going to be what? Positive or negative? Cl. Cl is negative and this is positive. So this molecule will orient itself in such a way that what is going to look or be next to it will be what type of charge? Delta positive and delta negative. Because the negative attracts the positive or vice versa. The force of attraction of this molecule to this molecule is called an intermolecular force. In that particular case, what is the force called? Is it ion-ion? Hello? Is it ion-ion?
I would say dipole.
It is not ion-ion because this is not an ionic compound. Is it ion-dipole? It is not ion-dipole because it's not ions, okay? How about this? I get HCl and I mix it with water. What type of force is present in there? Ion dipole. It is ion dipole because this HCl will dissolve in water to form H plus and Cl minus. And then this ion and this ion will be surrounded by water. Okay? So that is called ion dipole. We talked about dipole, and we talked about London dispersion forces. Yes? I omitted two of them. And the ones that I omitted are combinations of those. Okay, so we had a combination of ion-ion, and then we had ion-dipole, yes? And then we had dipole-dipole. And then we had something called London dispersion forces, which we are going to refer to as induced forces.
Okay.
What are the combinations am I missing?
Hydrogen bond.
Ion what? No, hydrogen bond. Only if you're a biologist, okay? Most of you are. Guys, what combinations are we missing? You guys never played this game? You missed your childhood, huh? I'm saying the London dispersion forces are not called the London, it's called induced dipole. What are the other combinations we can possibly have? Ion-induced dipole. I don't understand what the difficulty is, but ion-induced dipole. We don't have this one, yes? And then dipole-induced dipole. And of course, if we need two of these, the last one is going to be called induced dipole, induced dipole. Okay, the name for induced dipole is called London dispersion forces, yes? And this is the order of strength. Okay, the stronger one obviously is ion-ion. Now I want you to notice that when you have ion-ion forces, you have an example this. What is the bonding force in ion-ion forces? What is the bonding force in sodium chloride? What is it called? Ionic bonding. And what is the intermolecular force in sodium chloride called? Ion-ion. And is that different? Or is that the same attraction? It is the same. Because here you have a full positive and a full negative. So intermolecular force here is called ion-ion, but the bonding force is between the two ions still. And that is called an ionic bonding. So I want you to write this down. For ionic molecules, no, okay? For ionic compounds. Intermolecular forces and intramolecular forces are the same. The intermolecular force is called, what is it?
Ion-ion.
It's called ion-ion, while the intramolecular force is called ionic bond. Guys, do me a favor. Somebody sacrifice a sheet of paper and pass it around as attendance, please. She is sacrificing the piece of paper, so you don't need to do it twice. What's happening, man? That happens because you are here 10 minutes late, bro.
What had happened was, did you hear about that semi-truck that flipped?
No, I did not.
Well, you check the news afterwards, and if you find it, you let me know. Because that didn't happen.
It happened?
No, it didn't.
Because you know, nobody brings me here in a helicopter. I don't know if you understand that, right? I get up in the morning, I sleep like you, okay? I look all messed up, but I sleep. Alright, so now for this one here, this is what most books refer to as the first intermolecular force, okay? Some people say that this is not an intermolecular force because it is both intermolecular and intramolecular, okay? This is going to be in the MCAT, it will say ion-ion, so I teach it to you this way. Now, examples of ion-induced dipole. Maybe I shouldn't talk about this yet. I have to have an ionic compound. Of course, is this weaker or stronger than this?
Stronger.
It's supposed to be stronger. Okay, this is a full positive or negative charge, and then an induced dipole.
Partial.
And this is a dipole and an induced dipole. That should be a weaker force, okay? So, an example of this is iron. Yes? Iron and oxygen. Iron is an ion. Wait a minute. Oxygen polar or non-polar? This is polar?
O2.
Non-polar.
It's
How do you
non-polar.
know this is polar? Or non-polar? How do you know it's non-polar?
Because it's diatomic, they're equally distributing.
Okay, that's right. It is non-polar because it looks like that, yes? There is a plane of symmetry here. It has lots of oxygens, okay? It has a lot of oxygens, it has two of them, okay? But it's still non-polar because this thing is symmetrical, yes? Anything that is symmetrical will be non-polar no matter what it's made of. So, this iron and O2 is an example of ion-induced dipole. Is that important? Are you ever going to use this? Is that important for you to learn? No, don't put me.
Sounds like
I don't like to be the hero.
I assume it's got something to do with hemoglobin.
Something to do, that has all to do with hemoglobin. Okay? Everybody that has blood carries oxygen that way. Okay, not a cockroach. A cockroach does not have that type of thing. You know that a cockroach needs to, the oxygen needs to go from wherever they're breathing it to whatever side of their body by diffusion. Did you know that? Have you ever squished a cockroach? You ever see blood in there?
No.
So you have squished cockroaches. Why? You killed them. They didn't do anything to you.
Because I hate them.
Why you hate them?
They're disgusting.
But you don't need them yet. You don't need them. You just see them walking around. Why, they look bad? You discriminate against ugly people? Cockroaches give you bad allergies, okay? You might not know about it, but they give you bad allergies, believe me. Okay? So you should not have cockroaches in your house, okay? But if cockroaches had lungs like we do, guess what size they would be?
Very tiny.
They would be this size. If they were this size, we would not be here, okay? Believe me. There's more insects than anything else. And insects are not big, they are small. Only because of their respiratory system. If they breathe like us, we would be history. They're a lot better than we are killing things. So, dipole-induced dipole. An example of this, yes, this is the way we carry oxygen in our body. So is this important? This is the reason why you are alive.
Wait, that's dipole-induced dipole?
This?
Yeah.
No.
Okay.
This is ion, right? Ion.
It's ion non-polar.
Ion-induced dipole. Because this is non-polar, right? This is ion. And this is non-polar, right? And non-polar is induced dipole. And now this dipole is something that has a dipole like, let's say, ICL. Does that have a dipole? No?
Yes.
That has a dipole.
Mhm.
And CLCL does that have a dipole?
Nope.
It does not. So if those two things, now sometimes you have no way of knowing whether something dissolves or it doesn't. Okay, I don't care. All I'm going to give you is two different compounds, and I'm going to ask you, the force of attraction between them is going to look like what? Okay, that's what I'm going to ask. And what are the things you have to look for? You have to first find out if the compound is ionic. If it is ionic, what type of forces can it have? Ion or ion dipole. But for you to have an ion dipole, what do you have to have? You have to have ionic compounds or an acid together with something else. And that something else will be what type of compound? Polar compound. Okay? It will be a polar compound. Everybody has to know what a polar compound looks like. Okay? And if there's nothing ionic, but there is something that is polar, what could it be? It could be dipole-dipole. Or it could be, what else? It could be dipole-induced dipole, but that has to be together with another substance that is what? Non-polar. So basically, all you need to do to determine any of these forces is find out, is it ionic or is it polar? Only two questions. If it's ionic, it could be one of the ones that has ions. And if it's polar, it could be one of the ones that is polar. If it's not polar, what is it? If it's not polar, the molecule will be what? Non-polar, right? Yeah, so you only have to ask yourself, is it polar? Because if it's not polar, it will be non-polar. And it will be one of those. Okay? Unfortunately, there is more to that. And let's try to confuse you now.
Professor,
Yeah.
if it's non-polar, it's going to be one of the dipole ones?
If what?
You said if it's non-polar, it's gonna be one for what?
Induced dipole. Now, we were talking about an indication of the strength of intermolecular forces is the boiling point, yes?
Yes.
So which of the following should have a higher boiling point? Question on the test. Which of the following has a higher boiling point?
Ion.
No, I'm gonna give them to you. You tell me which one of those two. Yes, ion does. But I'm not gonna give you that chance. I'm gonna tell you.
Water.
Which of those two will have a higher boiling point?
Water.
What do you think? Question would be, which one is more what? They're both polar, yes? Question is, which is more polar? The first or the second? Water is more polar. Because water is more polar, it will have the higher boiling point.
And that's because of the difference in electronegativity, right?
No, that's because of the structure and because of the difference in electronegativity. Remember, there's something called the dipole moment, and that dipole moment has a lot to do with the structure, yes? Has a lot to do with the shape of this molecule. You don't have to do it for all, but you gotta have an idea. This side that I added to this here, is this side polar or non-polar? This side. Because let's say that this looks like this, yes? H2O looks like that. That side and this side is the same, yes? And that side and this side the same. This side is making this what? It's making that non-polar. Okay? Yes? Alright.
What's the other stuff? Acetic acid?
No, that's methanol. Alright. CH3O. CH3OH or CH3CH2OH. This is wood alcohol. This is drinking alcohol, the one you like to drink. You drink this, you are happy for a little bit at least. And if you drink this, you die. That's it. You want to kill yourself in a very bad, agonizing death. You drink a glass of that. That's it, you will die.
I'm kind of confused because I thought you said that CH3OH was polar, unless it has like carbons.
It is polar.
This is Germany working with more polar.
It almost going to be
Nice. If you compare me to a 3-year-old kid, I am strong. Yes? But if you compare me to Mr. USA, I am weak. Yes or no? So it's a comparison between things. This one is more polar than this one. This is not the most polar compound in the world. It is just more polar than this one. And why is this less polar than this one? Or more polar, why is this more polar than that? It's because this side here is non-polar. Okay? So from those two over there, which one would have the higher boiling point? Which one? Absolutely not. This is the higher boiling point. Now you are confused on why, yes? You are? Very good. And that was the purpose. The purpose is for you to be confused and for you to think, oh, I know stuff, and then I tell you, you don't. Alright. So, we are still talking about dipole forces, okay? Now my secretary, did she send you the notes, my secretary?
No.
It's too bad. I'm gonna send you slides for this, okay? PowerPoint slides. I had a picture there of this thing. In the dipole forces. Dipole forces increases with if a molecule has a bigger dipole, like this one, than that one. Should it have a higher boiling point? Yes, because of an increase in dipole forces. Now, this increase happens with polarity. The higher the polarity, the higher the what? The dipole force, yes or no?
Okay.
So, and this polarity is called dipole moment. So if I were to give you numbers for this dipole moment, will you be able to say this one is more polar than that one?
Yep.
Yes or no? Yes. So let's say I tell you compound X has a dipole moment. The dipole moment is mu. And the units for this are dBi. Okay? Don't worry about what that is, okay? You were supposed to have done it in 1045. Maybe your professor didn't. And let's say this is 1.5 that. Let's say Z has a dipole moment of 2.9. Okay? According to the dipole moment, which molecule is the more polar molecule from there? Z is the more polar molecule. And Z will feel the strongest what? Dipole forces. Because it feels the stronger dipole forces, Z will have the what? Hello?
Highest point.
Higher boiling point. From these three, yes?
Mm-hmm.
It will have the higher boiling point. You can only compare those three if the structure and the molecular weight is very, very similar. Okay, so I'm going to say the same. When it's not the same, it's just very similar. In order for you to do this, what do you need? Molecular weight and structure need to be very, very, very similar. If they are not similar, then you cannot compare the dipole moment. So let's say that I will say that this is molecular weight here. The molecular weight of this, let's say, is 50 grams per mole. And the molecular weight of this is 54 grams per mole. And the molecular weight of this is 52 grams per mole. Okay? And I'm going to show you the reason why that is now. Yes?
No.
You can only compare dipole moment if what? If the molecular weight is
And the structure is similar.
the same and the structure is more or less the same, yes? Maybe I should show. Questions about this?
I still don't see why that is.
Yeah, I'm not sure.
Because I haven't explained that yet. I explained this one, yes?
Mhm.
I have not explained that one. I just showed you what your confusion was going to be.
Would it be the same as the one that you were showing us last class with the carbon, the ratio like 4:1 for that one?
That has something to do with that, yeah.
Okay.
So, this here, this one has a higher dipole than this one, yes? Because of the structure and because, whatever, dipole moment. Okay? So this is about dipole forces. Now this here has the same OH, yes? But what is different is this chain. This has something to do with induced dipole forces. So that was dipole. And we are going to talk about how you increase the strength of London dispersion forces. So we are going to call these London dispersion forces. Now, what molecules feel London dispersion forces? All molecules, regardless of polarity. Yes?
Mm-hmm.
The only requirement for you to feel a London dispersion force is electrons. Okay? Everybody got electrons, so everybody feels London dispersion forces. So, now, does it make sense that the more electrons you have, the more London dispersion force you'll feel?
Yeah.
Does that make sense?
Mm-hmm.
Yes. So, and this has something to do with something called polarizability. Polarizability means how polarizable something is. Most of the time the word polarizability is used for London dispersion forces, because this here has a permanent dipole, okay? That in a London dispersion force, does it have a permanent dipole? No, because the molecules are, in general, are nonpolar. Yes? Guys, if someone had your ID number, what would they do with it? Not me, of course, but one of your friends. What would they do with it? Would they be able to do anything with it or no? They can, unless they have the password. And you won't give them the password unless you're sweet on each other, right? In which case you deserve it. All right. So everything feels London dispersion forces, yes or no? Most of the time, the only molecule that has only London dispersion forces, what type of molecule?
Nonpolar.
Nonpolar. In nonpolar molecules, do they feel dipole-dipole forces? No, they don't feel dipole-dipole forces. So nonpolar molecules only feel London dispersion forces. Now, when they are nonpolar, we talk about polarizability. And polarizability increases with the number of what? Of electrons. And the number of electrons increases in the periodic table with the number of protons. And the number of protons is increasing according to the molecular weight of this thing, okay? So, polarizability has something to do with molecular weight. Okay, the higher the molecular weight, the what the polarizability? The higher the polarizability. Because the higher the molecular weight, the more what you have. The higher the molecular weight, the more of what do you have? The more electrons, okay? So let's say I give you here an example of I2 and F2. Which one is more polarizable? I2 or F2? I2 is more polarizable because it has a higher molecular weight. F2 is less polarizable and has a lower molecular weight. As a result, which one should have a higher boiling point? I2 should have a higher boiling point. Now, this is only if the molecules are what? Non-polar. Because if they are polar, now you have two things in there. You have dipole-dipole and you have London dispersion forces. Yes or no?
Mm-hmm.
So when I look at this here, the dipole, let's say that the dipole for these two are going to be, is going to be the same. Okay? That this OH here and this OH is what determines the dipole for the whole thing. And this is polar and this is still polar. But what is this different from here? The molecular weight is different. Yes?
Okay. So that
Which one has a
greater
higher molecular weight?
The right side.
The one that has a CH3CH2 has a higher molecular weight. So this has a higher molecular weight. It should have a higher
Boiling point.
boiling point. This is because this OH here and this OH here was the same. Yes or no? The only difference there was the molecular weight. Which of those two should have a higher molecular weight and why? Cl4 or CH4? CCl4 has a higher boiling point. Why does it have a higher boiling point?
Greater molecular weight.
Because it has a higher molecular weight. And you can compare them because they are both what? They are both non-polar. They have more or less the same polarity, yes? But you can still compare molecular weight if they have more or less the same what? And the same structure. You can still talk about molecular weight if they have the same polarity. That's right. Just like we can talk about the different polarity if they have more or less the same molecular weight. And the reason why it has to have the same molecular weight is because of what? No, but why does this have to have the same molecular weight so I can compare those? Because if it has different molecular weight, then what happens? They have different London dispersion forces. They have different boiling points based on only this. So I make these the same so I can compare what's changing here, which is dipole moment, while the molecular weight is the same. Yes? Here, the structure has to be the same. And here I have to have the same what? Polarity for me to compare molecular weight. You're all staring at me, you're not writing it down. Because you didn't understand it, right? In order for you to compare molecular weight, you need very similar polarity. In order to compare dipole moments, you need very similar what? Molecular weight. So, would it be a fair question if I ask you to give me which of these two would have a higher boiling point?
No way.
Would it be fair for me to ask you which of those two would have a higher boiling point?
No.
No, it would not be fair. Because this one is more polar than that for sure, yes? More polar than that for sure. But this is very, very
High molecular weight.
non-polar and a very high molecular weight. So which one wins? Does the dipole moment win or does the molecular weight win? So which one wins? Well, I don't know. In this case, probably this one is going to win. Okay? Hmm? Because of the molecular weight is much, 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 much higher. But that's not what happens all the time. A fair question would be if I ask you something on the same group of the periodic table. Okay? Or I ask you, for example, let's do the easy one first, yes? According to molecular weight, which one do you expect to have a higher boiling point? H2SK. Now the reality is, which one has a higher boiling point? H2O has the higher boiling point.
Because it's far more polar, right?
Because what?
More polar.
Because H2O is a lot more polar. Not by a little, it has a higher polarity by a lot. Okay? Because H2O is very, very, very polar. Okay? And because H2O makes something that everybody has been waiting for, which is called a hydrogen bond. Okay? Which most people don't know anything about in this class, yes? Is a hydrogen bond a bond?
I wouldn't call it.
It's an attraction.
Yeah, it is an attraction. How do you know? You remember?
I think the Vista was the one that told me.
You what?
The Vista was the one that told me.
At least they're messing me up, man. We haven't talked about hydrogen bonds. We will in a second, okay? So this one has a higher boiling point because these are polar, okay? But in this case, this has a higher boiling point because of an abnormal strength in the intermolecular forces here, and they are dipole-dipole, specifically called hydrogen bonds, which I haven't talked about yet. Which of those two should have a higher boiling point? NH3 or PH3? NH3 has a higher boiling point. Once again, this has a higher boiling point because of the strength of the intermolecular forces or the polarity. Yes? Yeah.
And that's electronegativity alone, right? Like you're just comparing electronegativity to find out oxygen flowing.
Well, I am showing you two things. Yes, I'm showing you molecular weight, and I am showing not polarizability, polarity. There's two things in there, and I'm telling you that if they are in the same group, so far H2O1, so far NH3 because they feel something called hydrogen bonds. Okay? Now I give you another example, CH4 and SiH4. Which one has a higher boiling point?
Well, that's a non-polar, so I'm gonna go with silicon. What do we call it? Silicon?
Okay? That's right.
What?
This here has a higher boiling point.
What's the name of that?
I don't know, why do you want to know the name? Silicone. Some girls are made 30% silicone, right? That's what we care about, it's useful. So, now what happened here? What happened here is this is non-polar, this is non-polar. So the polarity of this is the same. Because of that, that molecular weight is the stronger force. Why did molecular weight become more important here?
Because of the much stronger polarity and intermolecular forces.
Because of the much stronger polarity of these two and the strength of the intermolecular force, which is called hydrogen bonds. And that is a special case. A hydrogen bond is a type of what force?
Intermolecular.
Yes, but a type of which ones? I already gave all to you. You gotta put them somewhere. Is it ion-ion forces?
Dipole, dipole.
Dipole-dipole, that's right. So, hydrogen bonds is a type of dipole-dipole force. Hydrogen bonds is a type of dipole forces. It is not a bonding force, it is a force of attraction. Okay? Now there's many people that are going to refer to this as a bonding force, the bond this, the bond that, because a bond is at the end a force of attraction anyway. It is true, a bond is a force of attraction, but they separate things into, for bonding, ionic bonds, covalent bonds, and metallic bonds. I don't even know what a metallic bond is. Do you guys know? You don't know?
Sounds like
Me neither. How am I supposed to know?
lattice?
No, lattice is ionic bonds. I forgot the password. What a weird life I have. One day I remember the password and the other day I don't. Okay, hydrogen bond is when you have a hydrogen directly attached to one of the following elements. Fluorine,
Oxygen,
oxygen,
nitrogen.
and nitrogen. Almost spells like fun, yes?
Yeah.
Fun. Almost fun. Should have been you here. Anyway, if you have a hydrogen directly attached to one of these, you will have hydrogen bonds, yes? Does this molecule make hydrogen bonds, H2O?
Yes.
Yes, it does make hydrogen bonds because it has an oxygen with what next to it? With a hydrogen attached to it. How about this? Does this make hydrogen bonds?
Yes.
Yes, there is the oxygen. And what does it have next to it? The hydrogen. Now, does this make the same amount of hydrogen bonds this makes? No, it doesn't. This makes more hydrogen bonds because it has more hydrogens attached to that oxygen.
Question.
Uh-huh.
Why doesn't chlorine make hydrogen bonds if it's the same electronegativity as nitrogen?
Because it doesn't have the lone pairs to use. Chlorine makes one bond to one.
Are hydrogen bonds stronger? Like, where do they range, like, in the strength? You know, we were
Well-
talking about the strengths of the other ones.
Okay, so write this down.
Okay.
If you want to rank them, and we are going to rank them, the ranking is, a hydrogen bond is the strongest of all dipole-dipole forces. So a hydrogen bond is stronger than a normal non-hydrogen bond dipole-dipole forces. So the subdivision will look like this. We are going to have dipole-dipole forces, yes? We're going to say that the strongest dipole-dipole forces are called hydrogen bonds. Okay, and then non-hydrogen bonds. So this molecule here is polar, but if it has hydrogen bonds, it will be stronger than a molecule that does not have hydrogen bonds.
Okay.
All right. Does this make hydrogen bonds, yes or no? Hello?
Yes.
It makes hydrogen bonds because there is a nitrogen with
Hydrogen.
a hydrogen directly attached to it. We are going to draw the hydrogen bond in a second.
Is there a difference in strength between the different hydrogen bonds, say between an oxygen hydrogen bond and nitrogen?
Yes, there is. Okay, so does this make hydrogen bonds?
No.
This
Yes.
does not make hydrogen bonds. Does not make hydrogen bonds because in order for you to make a hydrogen bond, the hydrogen needs to be directly attached to the fluorine. This hydrogen's,
Oh, this is the structure.
that's how that looks. The fluorine is attached to the carbon and the hydrogen is attached to the carbon. That does not make a hydrogen bond. What is the only example of hydrogen bonds to fluorine? HF is the only example of hydrogen bonds to fluorine.
But that doesn't have a lone pair either.
It doesn't, but it has a very large difference in polarity.
Okay.
So it's important to draw the structure to see that, because I wouldn't have saw that just like looking at
No, yeah, it's important to draw the structure, but then you don't have to draw it. Whenever you see a fluorine, the only time that it's going to make a hydrogen bond is if it has an H next to it. If it's something else with a fluorine, it's not going to do it. Yes? Does that make hydrogen bonds to itself? Hello? It does not make hydrogen bonds to itself. It has an oxygen, but it does not have hydrogens on it. Okay? Let's draw how a hydrogen bond looks like. A hydrogen bond, still dipole-dipole force, yes or no? So, it is the same thing we drew before. The same thing we drew the last class. Here we have the lone pair. What's going to position towards that lone pair? A hydrogen from another water molecule. The force of attraction between these two is abnormally strong. Okay? And a hydrogen bond is denoted by these little lines. Okay? So, next to this lone pair, what else are you going to have? You're going to have another hydrogen. And we are going to say that this is a hydrogen bond because we are going to go like this with those lines. That's a hydrogen bond. If it's a normal dipole-dipole force, most of the time you do not draw it that way. What's going to be pointing towards this hydrogen here?
Oxygen.
An oxygen. This is what we did last class. Okay? So there it is. So apparently this single water molecule did what? Made how many hydrogen bonds?
4.
This one. It appeared to have made 4 hydrogen bonds. The lone pairs here are doing a different job from the hydrogens here, yes? So the oxygen can give its electrons and participate in a hydrogen bond, or it can give the hydrogens and participate in a hydrogen bond. Can this participate in a hydrogen bond? This oxygen here cannot participate in a hydrogen bond? Not to itself, but to something else. Like to water. Can it participate in a hydrogen bond to water?
Yes.
So let's say I have H2O, where I have this. Can that participate in a hydrogen bond? Yes. You can have H here from the water. And you can have another H here from the water. So this molecule can participate in a hydrogen bond with something else, yes?
Yeah, by itself it would
It cannot do hydrogen bonds by itself.
Okay.
That needs to be very clear to you, okay? And that happens a lot in DNA. You have DNA, yes? You ever seen your DNA? You haven't?
In books.
Questions, guys? It's confusing? It's gonna get a whole lot worse, okay? I'm telling you. You don't go home and you study, you are going to get a 30 on the test. It's not a joke, okay? And on the final exam, you're gonna have this stuff again. And by the time you take that final exam, this is going to look to you like, what? So good luck to you, okay? I wish you the best. You have a bright career ahead of you. Hopefully you don't have a perfect 4.0. So I'm going to mess that up for you. All right. Just kidding, okay? You got to study that. This is acetone. Have you heard of acetone before? Yes. All girls have, yes? All girls have. That's acetone. Does it make hydrogen bonds with itself? No, it does not make hydrogen bonds with itself. So do you expect the boiling point of acetone to be high or to be low? Low, because it is dipole, yes? It is dipole-dipole. This has a dipole, yes? Is this polar or non-polar?
Polar.
Why is this polar? That's right, because it has 3 carbons to 1 oxygen. That is polar. Okay? It doesn't make hydrogen bonds. If it made hydrogen bonds, will it have a higher boiling point? Yes, because it's not hydrogen bonds, you do not expect that boiling point to be very high. And acetone does not have a high boiling point, yes? Because that's why you use it for your nail polish. But can this participate in hydrogen bonds?
Yes.
This can participate in hydrogen bonds. Can that participate in hydrogen bonds? In general, no. Because this does have lone pairs there, yes? But these lone pairs do not participate in hydrogen bonds most of the time. Okay, that's what he was asking before. Because fluorine does not like making more than one bond. Yes?
If acetone were to participate, it would be where the oxygen is, with other, with another molecule.
Yes.
Okay.
With a lone pair. Okay? So, make the hydrogen bonds for NH3. Draw the hydrogen bonds for NH3. Guys, I don't want to scare you, but more than likely we're going to have a test in 2 weeks, okay? What's going to point towards this nitrogen here?
Hydrogen.
Hydrogen from something else, yes?
Mm-hmm.
That something else could have here what? A nitrogen or? An oxygen or a fluorine, let's say. But, oh no, we're doing it with a nitrogen. And I am going to go like that, those little lines, that's a hydrogen bond. How strong is that?
Very strong.
Abnormally strong. And what's going to be pointing towards this hydrogen? Nitrogen. What's going to be pointing towards this? Nitrogen. And what's going to be pointing towards this?
Professor,
Yeah.
even if the hydrogens in the original structure didn't have lone pairs, they still make hydrogen bonds.
The hydrogens do not have lone pairs.
Right, but they still made hydrogen bonds all the way around.
Yeah.
Right, so it's not.
Because of a difference in electronegativity. That hydrogen is delta positive while the nitrogen is delta negative. Yes? But it needs to have lone pairs. What do you want to know? You want to know the reason?
No, you answered it, that's it. It doesn't matter whether.
I don't know what to say, man. God made it that way. It's not up to me to find out why He made it that way.
Professor,
Sure.
just one more time. In the case of the acetone, it's going to form hydrogen bond, right? With the
No.
oxygen?
With itself, no.
No, but with the.
With something else that has hydrogen bonds, yes.
Yes.
So I don't say that it forms hydrogen bonds. I say it can participate. The word that you should know is participate. Acetone can participate in hydrogen bonds, but it does not make hydrogen bonds with itself. Yes? That could be a question on the test. It's different to say participate than to make hydrogen bonds. Yes? To make, you are self-sufficient. Does this make hydrogen bonds? If you have a bucket of this, does that make hydrogen bonds in there? No. But if you mix that bucket with another bucket of water, does it make hydrogen bonds? Yeah, it participates in hydrogen bonds. This participates in hydrogen bonds. It does. If you had a carbon and a fluorine on it, that does not participate in hydrogen bonds, but it is polar, so it'll have some interaction, but it's not called hydrogen bond. It's called dipole-dipole. Yes?
Yes.
Which is weaker than a hydrogen bond. guys, you have to go on next week. You want a quiz next week? I'm gonna ask you questions about this next week. If you don't know, I'm gonna give you quizzes. Okay? All you need to do is study. I'm going to stare into your soul. Alright. Let's talk about surface tension. So let's say you have a beaker, and the molecules in here are called the bulk molecules. And they're called bulk because I guess there's a lot of them there, yeah? And you'd never guess what the molecules on the surface are called.
Surface molecules.
Surface molecules. I'm amazed. Oh, I forgot to tell you the strength of these forces, yes? It's gonna be on your slides. I'm gonna say it, don't write it down. The strength of a London dispersion force. The strength of a hydrogen bond is about 40 kilojoules per mole. Okay? It can range, right? But 40 kilojoules per mole. And the strength of a London dispersion force can go from like 0.05, let's say 0.5 or less than 1, to about 40. So how strong can London dispersion forces become? Very strong, yes? How do they become stronger? By the more carbons you have on it, or if you're talking about carbons. Most of the time we refer to nonpolar stuff as carbon, that's organic. So a London dispersion force can catch up to a hydrogen bond, okay? Because London dispersion forces are additive. Write it down. They are additive, meaning that the higher the molecular weight, the higher the London dispersion force. But polarity is something that it doesn't change, yes? If something is polar, it will be that polar and that's it. Why are you looking at the time? You want to go home, all right? So, if you have, let's say, a molecule with 5 carbons, and you have a molecule with 30 carbons, does such a thing exist? A molecule with 30 carbons? Yeah, why not? And a molecule with 50 carbons, which one would have a higher boiling point? The one with 50. And if you look at petroleum, fossil fuel, you have heard of that before?
Yep.
Some of these things are gases in there, and then comes liquids, and then the viscosity starts increasing and becomes more and thicker. Eventually you go from gasoline to diesel or kerosene, and then you go to oils, and then you go to wax, and then you go to tar. You ever seen that stuff?
It's gross.
You ever seen the tar? You see the black thing they put on the roof of your house? Have you ever gotten it on your hands?
It's freaking hot.
Girls haven't. Guys, no? Yes, you guys are. Okay, well, you get the stuff on your hands, my friends, and it's not going to go away. Like, you can put stuff on it, it will not dissolve. Okay? It won't dissolve in anything because they're too long and they cannot go into solution. That's the topic of the next chapter. Okay, for you to remove it from somewhere, you actually have to physically scrape it off. Okay, so whenever this oil is in the ocean and fish and birds get it on their feathers and skin, they will never get this off unless a human goes and takes it off little by little. So, you ever seen a pelican full of that stuff?
Mhm.
You have what? A dog? What about a dog? You eat dogs? What do you have done it to a dog? And the keys? Where? Okay. The dog is, okay, yeah, dog swimming in the ocean. So, surface molecules and bulk molecules. This molecule here, is it going to feel a force of attraction, yes or no? Is it going to feel a force of attraction to something else? Hello?
Yes.
The answer to, is something going to feel a force of attraction to something else, is always yes. It could be little, but it's yes. So is this going to feel a force of attraction? Yes. To the molecule on the top, to the molecule on the side, to this molecule here, to the molecule on the bottom. I don't know if you get the hint.
Mhm.
The net force of attraction, since it's been pulled in every way the same way, the net force of attraction is
0.
0. This is not attracted to one side more than it is to the other. But now these surface molecules here, where are they attracted to? Well, they're attracted to the molecule here, and they're attracted to the molecules that are below it. Yes or no? Are they attracted to any of the molecules up here? No. So what this does is the surface molecules, they get packed together closer because the net force of attraction is towards the bottom. Okay, so what that does is it makes the liquid harder to separate these molecules that are being attracted strongly. And that is called the surface tension. Hello?
I'm sure.
That is the reason why a water gliding spider can walk on water. You ever seen one walking on water?
Mhm.
You never seen one? Me neither. I've seen the Discovery Channel. You guys don't have cable?
So because it doesn't have those.
Because the molecules are tighter packed because they're being forced either down or to the side.
Okay.
In order for you to separate them, you have to overcome that force. So, of course, if one of us sticks a foot in the water, what's going to happen? You are going to kind of break that force, yes? But, you know, a spider that walks on water doesn't have a problem with that. You what?
I want to be a spider.
You want to be a spider? Good, man.
I'm a water walking spider.
You can actually,
could be Jesus.
you can make some, you know, if you take engineering classes and stuff like that, they have a competition, well, not here, but in another school, and the competition is to race across the lake on foot. So they make these shoes, right? Not shoes, but whatever instrument it is to walk on the water, right? And I used to watch them all the time, and all I ever wanted was for them to fall. And most of them did fall. So, I mean, that water is disgusting. I urinated a couple of times in that water. Just kidding. So, that's called surface tension, okay? Adhesive forces and cohesive forces.
A surface tension can form with cohesive forces?
They have something to do with that, right? Adhesive forces and cohesive forces. These are not intermolecular forces, but they are, but they're not. Adhesive, what's an adhesive bandage? You ever heard of that before? Like, I don't know the definition of this myself, but I know what an adhesive bandage
It
is,
has to
yes?
stick to the surface.
What do you stick it to? Do you stick it to itself or do you stick it to something else?
Something else.
To something else. So adhesive forces are those that attract molecules to another surface. Attraction of molecules to another surface. And cohesive forces are attract molecules or attraction to each other, yes? Yeah.
This tension, does that also kind of apply to the molecules that are right against the glass?
That what?
That are like right against the glass, or are they just being attracted to the molecules that's next to it?
Yeah, that's what we're going to talk about now. Molecules on the glass. Surface tension is a result of intermolecular forces as well. The more that these molecules like each other, the what the surface tension?
Greater.
The greater the surface tension, okay? So it increases with intermolecular forces. And I did not talk about the forces here on the glass. This is about cohesive and adhesive forces. So adhesive forces are those that attract molecules to another surface. And cohesive forces are those that attract molecules to each other. Okay? So let's say we have a narrow container. Or let's say we have a capillary. And what this is going to do is going to give you a meniscus that is U-shaped. You've seen this before?
Yeah.
That's called meniscus. Okay? Now the question here is, why did it do this? And the reason why it did this, because in the U-shaped meniscus like this, adhesive forces are greater than cohesive forces. Write it down. For the U-shaped meniscus, adhesive forces are greater than cohesive forces.
So like the molecules are sticking to the walls.
Yes.
Okay.
So what is happening here is this glass is made of silicon dioxide, and silicon dioxide is polar, okay? Because it has this oxygen. That's how silicon dioxide in glass looks like. That happens forever, okay? Very, very, very long. So what can this do here?
Participate.
It can participate in a hydrogen bond. It won't make one straight, but it can participate in a hydrogen bond. So does the water like it? The water likes it. And the water likes it a lot. So because of that, this is supposed to be like this, yes? Supposed to be like that. But it likes it so much that this water starts creeping up on the side of how much it likes it. And when it creeps up on the side, because it likes the glass so much, then that becomes the U-shaped meniscus. So the U-shaped meniscus is because adhesive forces are greater than cohesive forces.
That's
If you have a meniscus that looks like this, what does this mean? Cohesive forces are greater than adhesive forces. And this means that this liquid, or whatever you have here, does it like the glass?
not at all.
It wants to run away from the glass. What does it like more? It likes more itself. Can you identify with that? Some girls can, right? Come on, say the truth. It's all about you, girl.
What type of liquid would do that?
This is mercury. The liquid that does this is called the, well, there are not many examples, but mercury is one of them. So have you ever seen mercury? What does it like to do? It likes to hang around by itself. It runs away from everything all the time. You've seen it or no?
Yeah.
You guys have never played with mercury?
See it in
Yeah, when the temperature.
Yeah, the thermometer.
Pero
Right.
I mean, I don't know what's wrong with you guys, but when I was a kid, I used to find thermometers everywhere and break them and play with the mercury. Maybe this is why I have some brain disorder.
So that's why when mercury is used in thermometer, it's because the cohesive force is like so
No,
great.
that's not why. Mercury is used in thermometers because the temperature will expand it enough that we can read it in a narrow place. We can use other substances, but they expand and contract differently with temperature. Sometimes if it's too much, it'll be a thermometer this big. They're alcohol thermometers. So this is mercury, and if the adhesive and cohesive forces are more or less equal to each other, then how is the meniscus going to look? It's going to look flat. So you can tell more or less if the adhesive and cohesive forces are the same, they'll look kind of flat. If they're a little bit, the U-shaped meniscus is going to be a little bit bigger. If they don't like the surface where they are, it'll look a
What's the
little
name
bit
of that
better.
other meniscus? The one for yourself? What's the name of that other meniscus?
The U-shaped meniscus, they're both meniscus.
This one is acting differently.
One is concave and the other one is convex.
Let's not talk about that, please.
All right. What else is there?
Viscosity.
Have you seen the trees in California? Is it called redwood?
Oh, the really
Yeah.
tall,
That's it, what?
That are like 100, like 200-300 feet tall?
Yeah.
You imagine a tree 200-300 feet tall?
Yeah, it's really
How does that tree get water up there? Because in a building, you ever been in a building that is very high? What do they need to get the water up there?
Pressurized pipes.
They need pumps, yes? No pumps, no water. And water is not gonna go up into the sky for nothing, right? Try walking up 30 stairs on that tall building, 30 floors on a tall building, see how that feels. That's how water has to go through. So, how does the tree get the water up there without a pump?
negative pressures. I guess.
I don't know, it's a vacuum? No, how does it make a vacuum?
Well, my guess is that you have the trees always evaporating water, so that creates like not exactly a vacuum, but a difference in pressures makes the water in the bottom of the water.
Yeah, but how up does it go?
Apparently far enough to get to the leaves. So.
Oh yeah, for sure, the trees are living. Okay, one of the reasons it does it is because of this meniscus effect. Okay, they have very, very small, let's call them capillaries, yes?
Okay.
Okay, and because of these small capillaries, have you ever gotten a very small tube? It doesn't happen with a straw. We have capillaries here in the lab. You put it inside of a liquid and you take it out. The liquid goes inside the capillary. The capillary is small. Goes inside the capillary, stays in there, doesn't come out. Okay? That's called capillary action. Write it down. Capillary action. And the capillary action happens because of the meniscus, yes? And the meniscus happens because of adhesive forces are greater than cohesive forces. So yes, the trees use state-of-the-art vacuum system and they use state-of-the-art little capillaries inside of them to transport all this water.
So it's like maybe that water's gonna come back down.
Hmm?
Just goes up, does it come back down?
No, it does not. It's one way. Do you have such a thing in your body? You have capillaries in your body?
Yeah.
You have capillaries in your body. But you got a pump too, right?
Hearts.
You got a pump. that is beating, and so that your beats are running out. Whatever amount of beats. One day it will stop beating and you are going to die. Become warm food. So don't think you're special. Alright. What else? Viscosity. Guys, you gotta tell me the time. I'm so excited I don't notice when the class is over.
9:20, you have 20 minutes.
20 minutes left?
What?
Yeah.
9:40.
Yeah, we have
Yeah.
20 minutes left.
Well, big deal, 3 more minutes for whatever.
The amount of sound.
Guys, he wants to be in the class.
Or is it?
Okay, viscosity. Guys, viscosity is the resistance of a liquid to flow. You're missing it because you're talking. I'm not going to repeat it. Viscosity is the resistance of a liquid to flow.
I just think of the word viscous. It's like
Yeah, viscous, thick, like thick. Viscosity decreases with increasing temperature.
yeah.
So if something is somewhat thick and you heat it, what does it become? More fluidy, yes?
Like
It
fat.
can glide better.
Or it makes sense because there's no kinetic energy in the vibration.
So how does a liquid flow, which has something to do with viscosity? How does a liquid flow? So if you have one here, in order for this liquid to flow, molecules have to go past each other. Yes? Molecules have to go past each other. And in order for them to go past each other, what do they have to become? Overcome the force of attraction between them, yes? So the higher the intermolecular forces, the stronger the viscosity, or the higher the viscosity.
So it's related to molecular weight as well?
It's related to molecular weight for nonpolar compounds, and it's related to dipole moment for polar compounds.
So the higher the intermolecular forces?
The higher the viscosity.
And the higher the molecular weight.
No, the higher the viscosity does not mean the higher the molecular weight. The higher the molecular weight for nonpolar molecules. But not the higher the molecular weight for polar molecules, it's not the same.
So can you repeat the last one?
Okay, I'm going to say it again, okay? Now, everything does not have a straight answer. Do you understand that? Everything is not just a yes or no. Sometimes it's sometimes yes, sometimes no. It's like a girl, right? Says no, but it's yes. Just that sort of stuff. You can understand that. So, viscosity increases with intermolecular forces. With an increase in intermolecular forces. Yes? Now, intermolecular forces do not increase all the time with molecular weight, yes? Yes or no? Sometimes, if you're comparing something polar with a higher molecular weight, the one polar sometimes wins, yes? Then I show you that? What has a higher boiling point? H2O or this? What has has a higher boiling point? H2O or that?
H2O.
Hello? Why does H2O have a higher boiling point? Because the molecular weight of this is 18 grams per mole. And the molecular weight of that is, how much is 12 times 3? Plus 8.
But,
45? Okay, whatever, okay? So, let's say the molecular weight for this is 44 grams per mole. Which one has a higher boiling point according to molecular weight? This should have a higher boiling point. So it's not about molecular weight. It's not even close. The stuff is a gas. Okay, this is propane. You use it for the barbecue. Okay? So stuff is completely a gas. Very, very, very low molecular weight. I mean a very low boiling point, and this has a very high boiling point. It's a liquid. Boils at 100. So this is by far a lot. It's not because of molecular weight. It is because of
intermolecular forces.
intermolecular forces, but because this forms dipole-dipole forces. Hydrogen bonds in particular. Okay? Alright. You know, I forgot to talk about something. Let's talk about we have 25 minutes, right? Big deal. 20 minutes extra, that's fine. So, here's what it is. I forgot to tell you. We talked about the same molecular weight. We talked about the same polarity, but I forgot to talk about the same structure, yes? Okay. Most of the time, the structure has something to do with London dispersion forces, okay? So, we have something like this. Question is, which of those two will have a higher boiling point? And this will go to organic chemistry 1 or organic chemistry 2 and for the rest of your life.
The linear one. So the carbon get to interact with the London dispersion force.
That's right. This molecule here has the same molecular weight that this has, yes?
Mm-hmm.
So, the molecular weight of this and the molecular weight of that is the same. Okay? So, it has to, the difference has to come from the structure. And this has a higher boiling point. So, linear looking molecules will have a higher boiling point than these type of molecules, which are called the branched. Okay? So this is called branched. And this is called linear. Linear has a higher boiling point. So what does branching do to the boiling point?
Decreases.
Decreases the boiling point. So branching decreases the boiling point. These have the same molecular weight. They have almost the same polarity or very close polarity. So why is it that this has a higher boiling point? Because of the shape. And the reason for that is because I can align, let's say a molecule looks like this, yes? I can align another of those molecules right on top of it. And it will interact all over the place. This attraction all over the place will lead to a higher boiling point. But when you have something that looks like this, and you put another bulb next to it, how many places do they touch each other? Okay? Only there. So the interaction is smaller because of branching. Less interaction in branching. More interaction in a linear molecule.
So if you were to ask about this, you would give us like a structure and a
Yeah, I give you those two structures.
And
Let's
we
say.
just have to know the difference.
Yeah.
Okay.
I give you those two and I ask you which one has a higher boiling point. You choose the one that is linear. And if I ask you why is the linear one, why does the linear one have a higher boiling point? Because of more
Structure.
interaction between them. I have a friend that is going to medical school at UM, and half of the things they talk about in a class, they were talking about mutations, they were talking about, this biology, yes? Can be explained with intermolecular forces. So the guy is listening to the guy and he goes, oh damn, that's intermolecular forces. So he felt compelled to call me. And say, hey Garcia, intermolecular force is still after me. But he's one good student. You guys are not going to remember intermolecular forces, so to you it's going to look like what? Like I never talked about it, right? If you don't know it, you can never use it, yes? Go to a pharmacist and say to the pharmacist, hey, how often do you use chemistry here? Like 1046 or organic, how often do you use it? He will tell you or she will tell you, never, we don't need that. And then that's when you ask, do you know it? And they'll go, no, I don't know any chemistry. Because if you know it, you use it. Guess how often I use it? Every day. Okay, guys. I'm gonna send you the slides, okay? Hopefully my secretary is in a good mood today. Okay, you can stop that.